Radiant energy propagation can be considered either from the classical electromagnetic wave theory or from quantum mechanical theory. And electromagnetic radiation follows the laws for waves oscillating perpendicular to their direction of travel. The propagation speed for electromagnetic radiation in vacuum is the same as the speed of light in vacuum, which is about 3 times 10 to the 8 meter per second. The speed in a medium is always less than c0, which is the speed in a vacuum. The index of refraction is the ratio of the speed of light in vacuum to the speed in a given medium. And so as you can see, for glass as an example, the index of refraction is 1.55. For some gases, it's approximately 1. For media that attenuate, and attenuation mean absorb and scatter, so let's just put that here. Radiation during propagation, a quantity called the complex index of refraction is often used. We're not really going to deal with volumetric radiation in enough detail for us to look at the complex index of refraction, although we'll point out how it's used in later sections. Electromagnetic waves can be classified by wavelength in vacuum or its reciprocal, which is the wave number, or in terms of the frequency. So the relationship is this: lambda, which is the wavelength, times the frequency is equal to the speed of sound. So this is the basic operating equation that we can use to understand these problems. Let's just write this down again. Wavelength, which has units, for example, of meters. Nu is the frequency, which has units of inverse second. And so you can see that relationship holding. And of course, lambda 0, the wavelength in vacuum, is related to the speed of light in the vacuum divided by the frequency. Oftentimes we're going to measure using the micrometer scale. So we will typically measure wavelengths in terms of the micrometer, or sometimes called the micron, and it's 10 to the minus 6 meter. And later on, we're going to show a chart of radiation spectrum in the following slide. The wavelength of interest for us typically includes long wavelength ultraviolet, visible radiation, which is between 0.4 micrometers and 0.7 micrometer, and infrared to about 1,000 micrometer. 1,000 micrometer is a meaningful temperature because this corresponds to the approximate background temperature of the universe. So the background temperature of the universe is about 3 or 4 Kelvin. And we'll see that there's a relationship called Wien's displacement law that allows us to approximate the temperatures associated with different wavelengths using something called the Planck distribution. As we look at the electromagnetic spectrum, we see that visible light is this 0.4 to 0.7 micrometer. This is going to be interesting because our sun has a temperature of approximately 6,000 Kelvin, and we'll see that this 6,000 Kelvin is a meaningful representation for this Wien's displacement law to identify where our visible spectrum is. Said differently, one might imagine that life on Earth is particularly tuned to the solar radiation and the particular wavelengths and frequencies associated with it. So when we are interested in visible radiation, we understand what the source is associated with it. Infrared radiation, which is, so the scale that we're using here is micrometer. So as we go to longer wavelength systems to the right here, we are dealing with lower temperature sources, less energetic sources. As we mentioned, approximately near 1,000 corresponds to this background temperature of the universe. And radio, radar, TV type wavelengths are much lower energy, lower temperature, if you will. Whereas we see that as we look at ultraviolet and higher energy, so these are higher energy and higher effective temperature sources correspond to these smaller wavelengths. And so we see that something, for example, at about 10 to the minus 2 here corresponds to 300,000 or something corresponding to about a 30 electron volt condition. So these are very high energy conditions to the left of visible. There are particular transitions that allow these. So the source of this radiation can be thought of as energy transitions, either within solid materials, within gases, etc. And so as we look at the infrared or visible regime here, these are electronic transitions in gases, whereas as we look in the IR, in the infrared, these are either vibrational rotational transition or rotational transitions in gases and lattice vibrations in solids. So there are vibrations or energy transitions that are occurring that are liberating these notional particles called photons, and it's these photons that we might imagine correspond to the electromagnetic spectrum or the electromagnetic output and radiation from these materials. As we look at very high energy systems, we see that it's either electron bombardment or radioactive disintegration that are the sources of these extremely high energy photons, and these very low energy photons are electronic circuit oscillations. So there's a wide range of physics that allow these electromagnetic processes to occur. We're going to be looking at two different ranges of interactions as far as the radiation heat transfer. We're going to mostly focus on surface radiation processes, and surface radiation means that we're looking at transfers between surfaces. So if I had a hot surface and a cold surface over here, all the photons or radiation that would take place from this hot surface, say, to the cold surface, and the cold surface is of course radiating also, we say that there is no attenuation, so no losses in the surface radiation problem. So it's called a non-participating medium. So the medium does not affect, so it could be either in a vacuum, or it could have a gas like oxygen, nitrogen, the components of air that over moderate path lengths do not attenuate, do not change in any way the energy transfer rate. Now we contrast that with so-called volumetric radiation. And so volumetric radiation, certainly there is a case where all of a sudden the gases participate. And so one obvious case of this might be a fire. So as we have something, a fuel packet burning and a fire, we understand that we feel the heat from this combustion process, even though we know that there's no, and we know there may not be solid particles in there. There could be very small solid particles, for example, soot particles, but oftentimes, even if we just had the products of combustion, water vapor and CO2, these are radiatively participating gases. And in those situations, we actually do feel the heat from the fire in the absence of surfaces. So in fire situations, in furnaces, we have to deal with volumetric radiation as compared to surface radiation in relatively clean heat transfer systems. And so space is another example where surface radiation or radiation in vacuum is applicable and is important. So the interaction, excuse me, the interaction of radiant energy, excuse me, the interaction of radiant energy with the surface depends not only on the surface properties, but also on the properties of the material below it. Oftentimes we think about surface radiation as occurring really within a micrometer or less of the surface, because the lattice waves within the surface, any photons that are released are strongly captured in distances that are very small compared to some interparticle spacing there. So these are really surface phenomena that we're dealing with. And incident radiation, so the radiation that comes from somewhere else that's incident on the surface, there are many things that can happen to it. It can either be transmitted through the material or it can be reflected. And the transmitted radiation can be partially absorbed in the body. So there's the possibility that we get some sort of attenuation law within the body itself. When there's strong internal absorption, this means that the transmitted radiation is completely absorbed on scales that are very small compared to the body characteristic length. And so different materials have this property. So metals have very strong internal absorption and so have good reflection properties. But once the material is once the photons are within the material, but are poor absorbers of incident radiation, and that's where their radiation reflection properties come into place. Depending on the wavelength of the incident radiation, so this is wavelength specific, a glass window can be a good transmitter but a poor absorber, but in different wavelength intervals it may be a terrible transmitter and a relatively good absorber. An opaque body absorbs all radiation passing into the body, and we talk about an idealization called the black body, which allows all incident radiation to pass into it, that is, it's not reflected, and it internally absorbs all the incident radiation, that is, no transmitted energy. So if we look at the basic energy balances in radiation, we see that incident radiation on the left here can either be reflected, absorbed, and transmitted, which is considered a partially transmitting medium, or it can be completely absorbed in the material, which is considered an opaque medium. And an opaque medium with zero reflection is considered a black body. So a black body is an opaque medium with no reflection. So all incident radiation is absorbed.